Hi, my name is Nehal Reddy, student number s4066394.
Hi, my name is Love Kumar and my student ID is s4040088.
Our is called Escape, the AI Survival Challenge. It is a Unity game developed using reinforcement learning with Unity ML agents. The main idea of the game is that the frog must survive in a hazardous environment and reach the flag before the timer runs out.
The game can be played manually by a user, but it can also be played by an AI controlled frog using trained ML agent models. In this video, we will explain the game design, the reinforcement learning setup, the different training stages, the final model result, and the limitations we found throughout testing.
The objective of a game is for the frog to reach the flag before the timer runs out while staying alive and managing its energy. The frog starts with 3 hearts, so health is an important part of the gameplay. There are different types of obstacles in the environment. The snake and rock both reduce health but do not behave the same way. The snake is more dangerous because it chases a frog and removes one full heart on collision. Rocks are smaller hazards and remove half a heart. This gives the game different levels of risk instead of treating every hazard the same. Mud is also handled differently from the other hazards. It does not reduce health. Instead, it slows the frog down, which makes movement more difficult and can indirectly affect survival because the frog may lose time or energy while moving through mud. Energy is another important rule. The frog loses energy while moving, and flies restore energy. This makes the game more strategic because the frog cannot simply move toward the flag forever. It may need to recover energy first. Overall, the game includes manual gameplay and AI control, which allows us to compare player control with the trained agent.
We significantly expanded the original frog game. The most important enhancement is the ML agent controlled frog. Instead of only being a manually controlled character, the frog can now be controlled by a trained neural network model. We also added procedural or random hazard placement. This means the environment is not always fixed, and the frog cannot rely on exactly the same layout every time. This makes the game and the training problem more challenging. Another major enhancement is the snake chase behavior. The snake is not just a static obstacle, it reacts to the frog and creates pressure during gameplay. Along with that, we added a timer, health system, energy system, flies, mud, win and lose conditions, and 3 difficulty levels. These conditions change the project from a simple movement game into a survival style game. The frog has to reach the goal, but it also needs to avoid hazards, manage energy, and handle different movement conditions. This is what made the final reinforcement task more interesting and more difficult.
In our reinforcement learning setup, the frog is the agent. The agent is the character that learns from the environment. Its goal is to reach the flag while avoiding hazards and managing energy. We used a discrete action space with 5 possible actions: stay, move up, move down, move left, and move right. This action design matches the movement style of the frog and keeps the learning problem manageable. The reinforcement learning loop works in stages. The first is the frog observes the current game state. These observations are passed into the neural network policy. The policy then selects an action such as moving towards the flag or staying still. After the action is performed in Unity, the agent receives a reward or penalty depending on what has happened. For example, moving close to the flag is encouraged, reaching the flag is rewarded, hitting hazard is penalized, and collecting flies is rewarded. Over many training episodes, the policy is updated so the frog can improve its behavior. We used Unity ML agents with PPO because it is a standard reinforcement learning approach used in the course workshops. The observation design was one of the most important parts of our ML implementation. Observations are important the information the agent receives from the environment. If the agent does not observe the right information, it cannot learn the behavior we expect to do. In the earlier versions, the observations were focused on simple navigations. The frog observed its own position, the flag position, the direction to the flag, and its velocity. This was enough for the basic V1 model because the task was only move forward towards the flag. However, the final game becomes more complex. The frog now has energy, flies, hazards, mud, and a chasing snake. Because of this, we expanded the final V3 observation size to 12. The important additions were energy percentage, direction to the nearest fly, and distance to the nearest fly. This change was necessary because energy affects the agent's decisions. If the frog only knows where the flag is, it may continue moving towards the flag even when the energy is almost empty. By giving it energy and the nearest fly information, the model has the information needed to start learning energy recovery behavior. This is why the observation design directly connects to the final game mechanism.
The reward system was designed to guide the frog towards useful behavior. In reinforcement learning, the agent does not automatically know what is good or bad. It learns based on the rewards and penalties we give it. The frog receives a positive reward for reaching the flag because that is the main objective of the game. We also add a small step penalty. The reason for this, we do not want frog to wander forever. The step penalty encourages the agent to finish the task more efficiently. We also used a progress reward. This means the frog gets encouraged when it moves closer to the flag. This helps learning because the agent does not need to wait until it reaches the flag to receive useful feedback. It can learn gradually that moving in the correct direction is beneficial. Hazards give negative reward because the frog should avoid them. For the final version, we added fly collection reward and a low energy fly seeking reward. These were very important because the final task is not only about reaching the flag, the frog also needs to manage energy. So the reward design balances several behaviors, reaching the goal, moving efficiently, avoiding hazards, and recovering energy when needed. We trained the agent in stages because the final game was too complex to build and train all at once. Instead of immediately training the frog in the full game environment, we used an iterative process. The first one was V1 trained by Nihal. This was a basic goal reaching model with the frog flag and walls. The purpose of V1 was to perform the ML agent setup worked and that the frog could learn simple movement toward the goal. The second version was V2, which I trained. In this version, rogues were added as hazard. This made the environment harder because the frog had to learn with penalty objects, not just move directly to the flag. The final version was V3. This combined the lessons from V1 and V2 and added the full game mechanics: snake, rocks, mud, flies, energy, and procedural placement. This stage process was useful because each version tested a different level of complexity. It also gave us preliminary experiments and later experiments to compare, instead of only showing one final result.
My V1 model was the first training experiment. The aim was to train the frog to reach flag in a simple environment. At this stage, the environment contained only the frog, the flag, and the walls. We kept the first model simple on purpose because before adding hazards, energy, and other mechanics, we needed to confirm that the ML agent setup was working correctly. This included checking that observations were being collected, actions were controlling the frog, rewards were being applied, and the model could be exported after training. The TensorBoard result for V1 showed that the agent was able to learn basic goal-reaching behavior. The model was exported as Nihal underscore frog agent underscore V1.ONNX. This became our baseline model. It was not the final game solution, but it was an important preliminary experiment because it proved that the core reinforcement learning pipeline was working. V1 also helped us understand that the frog could learn movement behavior when the task was clear and simple. After this, we were able to add more difficulty in the next model.
My V2 model built on the V1 setup by adding rock hazards. The aim was still for the frog to reach the flag, but now it had to avoid rocks as well. This made the environment more realistic and more challenging than the basic V1 scene. The key machine learning change was the hazard penalty. When the frog touched a rock, it received a negative reward and the episode ended. This forced the agent to learn that not every direct path to the flag is safe. It had to learn goal-reaching behavior while also considering danger. The TensorBoard graph for V2 showed a cleaner improvement trend compared with the start of training. The reward still fluctuated because the frog sometimes failed by hitting rocks, but the overall behavior improved in the hazard environment. This model was exported as Love Frog Agent V2 Rocks.onX. V2 was important because it was an intermediate experiment. It showed that the game should still learn with hazards were added, and it prepared us for more complex version.
For the final V3 model, we moved from the simplified training scenes into the complete frog escape environment. This version includes the snakes, rocks, muds, flies, flag, energy system, and procedural placement. This final setup was much more difficult than V1 and V2 since the agent had multiple things to consider at the same time. It had to move towards the flag, avoid hazards, deal with the mud, slow down, manage energy, and use flies for recovery. The training run used the behavior named frog agent. The observation size was 12 because of the added energy and nearest fly observations. The action space remained 5 discrete actions: stay, up, down, left, and right. During the training, the model field was set to none because the agent was still learning. We also added Game Manager training mode. This was a practical but important fix. In normal gameplay, the menu, win screen, or lose screen can pause the game. During ML training, that would interrupt learning. Training mode allowed the agent to continue episodes properly without the game UI stopping the process. The final run ID was final underscore frog underscore V3 underscore energy underscore flies underscore test 3. This gave us TensorBoard logs and exported checkpoints for the final model.
Difficulty levels. We also added 3 difficulty levels: easy, medium, and hard. This was added to make the game more complete and replayable instead of having only one fixed setup. The difficulty levels change the challenge of the same final scene. Easy gives the player more time and a more forgiving setup. Medium is balanced default difficulty. Hard increases the pressure by reducing time, increasing energy drain, making the snake faster, and making mud more punishing. These features make matters for a game design because it shows that the project is not only a training scene for ML, it is also a playable game with adjustable difficulties. The same core mechanics remain, but the player experience changes depending on the selected difficulty. For future work, the difficulty system could also be connected more deeply with machine learning by training separate models for easy, medium, and hard. That could make the AI better adapted to each version of the game. Final V3 agent. After training, the final model was exported as Final Frog Agent v3.onx and assigned to the Frog agent in Unity. For gameplay testing, the behavior type was changed to inference only. This means the frog is controlled by the trained neural network and model instead of keyboard input. The final V3 model is different from the earlier models because it is being used in the complete game environment. V1 was the basic goal reaching and V2 added rock hazards. V3 has to handle several objects at once. It attempts to reach the flag, avoids hazards, respond to energy, and use fly information. This is why the final model should not be judged only by whether it performs perfectly. It is solving a much harder task. The important point is that our final agent uses the expanded observation design and final reward system inside the full game environment. The final model demonstrates AI control in the game, and it shows how the project moved from simple navigation towards a more complex survival style reinforcement learning problem.
This graph shows the cumulative reward for the final V3 training run. The result is very important since it gives us an honest view of how the final model performed. Compared with V1 and V2, the V3 reward stayed negative. However, it did show a small upward trend. The reward improved from around -1.01 to around -0.94. This means that the model showed early learning, but it did not become fully reliable within our training time. We do not present this as a perfect final performance. Instead, we analyze why this happened. V3 was much harder because the environment included energy, flies, snakes, rocks, mud, and procedural placement. The agent had to balance multiple behaviors at once, and successful flag completion became harder to achieve consistently. This graph supports our critical analysis. It shows that the simpler V1 and V2 models learned more clearly, while the final V3 model needed longer training and better reward tuning. This is an important finding from a project, not something we wanted to hide.
This slide shows one of the most interesting behaviors from the final V3 model. In this example, the frog energy becomes critically low. Instead of only moving toward the flag, the agent starts moving toward a nearby fly. This behavior is important because it connects directly to the final observation and reward design. We added energy percentage, nearest fly directions, and nearest fly distance so the agent would have the information needed for energy recovery. We also added rewards to fly collection and for moving towards fly when energy is low. In this attempt, the frog does not reach the fly in time and the energy reaches zero. So the episode ends unsuccessfully. However, we included this clip because it shows that the final agent started reacting to the low energy state. The behavior is not fully reliable, but it is evidence that the final model was attempting a more complex decision than simple goal reaching. This also shows one of our main limitations. Energy recovery needs more training and more reward tuning so the frog can reliably choose and reach flies before energy runs out.
This final slide summarizes our critical analysis. The main challenge was that the final V3 environment was much harder than the V1 and V2. V1 only needed to learn basic goal reaching, and V2 added rock hazards. V3 combined energy, flies, snakes, rocks, and mud, and the procedural placement into one environment. Because of this, the final reward stayed negative even though it showed a small upward trend. We do not treat this as a simple failure. Instead, we understand it as early learning in a more difficult full game task.
Several design decisions came from this challenge. We increased the observation size from 8 to 12 so the agent could observe energy and nearest fly information. We added fly reward and low energy fly seeking reward to support energy recovery behavior. We also used training mode so the menu, win screen, and lose screen would not pose ML training. Another design decision was to keep mud ash slow down mechanic only, instead of making it another health damage hazard.
For future work, we would train the V3 model for longer, tune the rewards for successful fly collection, and add stronger hazard distance observations. The final model might also improve if we train separate models for easy, medium, and hard difficulty levels instead of using one model for the whole game.
Overall, our project demonstrates an iterative reinforcement learning process. We started with a simple frog to flag agent, added hazard learning, and then moved into a full survival style AI game. The final model is not perfect, but the project shows meaningful ML development, experimentations, analysis, and future improvement directions. Thank you.
Thank you.